Section 1. Determining relative age. Geologists estimate the Earth is about 4.6 billion years old. The idea that the Earth is billions of years old originated with the work of James Hutton, an 18th century Scottish physician and farmer. Hutton, who is shown in Figure 1, wrote about agriculture, weather, climate, physics, and even philosophy. Hutton was also a keen observer of geologic change taking place on his farm. Using scientific methods, Hutton drew conclusions based on his observations. Today, he is most famous for his ideas and writing about geology. Uniformitarianism. Hutton theorized that the same forces that changed the landscape on his farm had changed the Earth's surface in the past. He thought that by studying the present, people could learn about the Earth's history. Hutton's principle of uniformitarianism is that current geologic processes such as volcanism and erosion are the same processes that were at work in the past. This principle is one of the basic foundations of science of geology. Geologists later referred to Hutton's idea by pointing that although the processes of the past and the present are the same, the rates of processes may vary. Earth's age. Before Hutton's research was completed, many people thought the Earth was about 6,000 years old. They also thought all geologic features had formed at the same time. Hutton's principle of uniformitarianism raised some serious questions about the Earth's age. Hutton observed that the forces that changed the land on his farm operated very slowly. He reasoned that millions of years must be needed for these same forces to create the complicated rock structures observed in the Earth's crust. He concluded that the Earth must be much older than previously thought. Hutton's observations and conclusions about the conclusions about the age of the Earth encouraged other scientists to learn more about the Earth's history. One way to learn about the Earth's past is to determine the order in which rock layers and other rock structures formed. Relative age. In the same way that a history book shows the order of events, layers of rock, called strata, show the sequence of events that took place in the past. Using a few basic principles, scientists can determine the order in which rock layers formed. Once they know the order, a relative age can be determined for each rock layer. Relative age indicates that one rock layer is older or younger than other layers, but does not indicate the rock's age in years. Various types of rock form layers. Igneous rocks form layers when successive lava flows stack on top of each other. Some type of metamorphic rock, such as marble, also have layers. To determine the relative age of rocks, however, scientists commonly study the layers in sedimentary rock, such as those in Figure 2. The law of superposition. Sedimentary rocks form when new sediments are deposited on top of old layers of sediment. As the sediments accumulate, they are compressed and hardened into sedimentary rock layers, which are called beds. The boundary between two beds is called a bedding plane. Scientists use a basic principle called the law of superposition to determine the relative age of layers of sedimentary rock. The law of superposition is that an undeformed sedimentary rock layer is older than the layers above it and younger than the layers below it. According to the law of superposition, layer A, shown in Figure 3, was the first layer deposited, and thus it is the oldest layer. The last layer to be deposited is layer D, and thus it is the youngest layer. Principle of original horizontality. Scientists also know that sedimentary rocks generally form in horizontal layers. The principle of original horizontality is that sedimentary rocks left undisturbed will remain horizontal layers. Therefore, scientists can assume that sedimentary rock layers that are not horizontal have been tilted or deformed by crustal movements that happened after the layers formed. In some cases, tectonic forces push older layers on top of younger layers, of younger ones, or overturn a group of rock layers. In such cases, the law of superposition cannot be easily applied. So scientists must look for clues to the original position of the layers and then apply the law of superposition. Graded bedding. Heavy particles settle to the bottom of the lake or a river faster than smaller particles do and create graded beddings like this. Cross beds. As sand slides down the slope of a large sand dune, the sand forms slanting layers like the one shown here. Ripple marks. When waves move back and forth on a beach, ripple marks like these commonly form. Graded bedding. One principal clue to the original position of the rock layers is the size of the particles in the layers. In some depositional environments, the largest particles of the sediment are deposited in the bottom layers, as shown in Figure 4. The arrangement of layers in which coarse and heavy particles are located in the bottom layers is called graded bedding. If a larger particle are located on top layers, the layers must have been overturned by tectonic forces. Crossbeds. Another clue to the original position of the rock layers is the shape of the bedding planes. When sand is deposited, sandy sediments form curved beds at an angle to the bedding plane. These beds are called crossbeds and are shown in Figure 4. The tops of these layers commonly erode before new layers are deposited, so the sediment appears to be curved at the bottom of the layers and to be cut off at the top. By studying the shape of the crossbeds, scientists can determine the original position of these layers. Ripple marks. Ripple marks are small waves that form on the surface of sand because of the action of water or wind. When the sand becomes sandstone, ripple marks may be preserved, as shown in Figure 4. In undisturbed sedimentary rock layers, the crest of the ripple marks are pointed upward. By examining the orientation of the ripple marks, scientists can establish the original arrangement of rock layers. The relative age of the rocks can then be determined by using the law of superposition. Unconformities. Movement of the Earth's crust can be lifted. Movements of Earth's crust can lift up rock layers that were buried and expose them to erosion. Then, if sediments are deposited, new rock layers form in place of eroded layers. The missing rock layers create a break in geologic record in the same way that pages missing from a book create a break in a story. A break in the geologic record is called an unconformity. An unconformity shows that deposition stopped for a period of time, and rock may have been removed by erosion before deposition resumed. As shown in Figure 1, there are three types of unconformities. An unconformity in which stratified rocks rest upon unstratified rocks is called a nonconformity. The boundary between a set of tilted layers and the set of horizontal layers is called an angular unconformity. The boundary between horizontal layers of old sedimentary rock and younger overlying rocks that are deposited on an eroded surface is called a disconformity. According to the law of superposition, all the rocks beneath the unconformity are older than the rocks above the unconformity. Nonconformity. Unstratified igneous or metamorphic rock may be uplifted to the Earth's surface by crustal movement. Once the rock is exposed, it erodes. Sediments may be deposited on the eroded surface. The boundary between the new sedimentary rock and the igneous or metamorphic rock is a nonconformity. The boundary represents an unknown period of time during which older rock was eroded. Angular unconformity. An angular unconformity forms when rock deposited in horizontal layers is folded or tilted and then eroded. When erosion stops, a new horizontal layer is deposited on top of a tilted layer. When the bedding planes of the older rock layers are not parallel to those in younger rock layers deposited above them, an angular unconformity results. Disconformity. Sometimes layers of sediments are uplifted without folding or tilting and are eroded. Eventually, all of the area subsides and deposition resumes. The layers on either side of the boundary are nearly horizontal, although the rock layers look as if they were deposited continuously. A large time gap exists where the upper and lower layers meet. This gap is known as a disconformity. Cross-cutting relationships. When rock layers have been disturbed by faults or intrusions, determining relative age may be difficult. A fault is a break or a crack in the Earth's crust along which rocks shift their position. An intrusion is a mass of igneous rock that forms when magma is injected into the rock and then cools and solidifies. In such cases, scientists may apply the law of cross-cutting relationships. The law of cross-cutting relationships is that a fault or igneous intrusions is always younger than the rock layers it cuts through. If a fault or an intrusion cuts through an unconformity, the fault or intrusion is younger than all the rocks it cuts through above and below the unconformity. Figure 5 shows a series of rock layers that contain both a fault and an igneous intrusion. As you can see, an intrusion cuts across layers A, B, and C. According to the law of cross-cutting relationships, the intrusion is younger than layers A, B, and C. The fault is younger than the intrusion of all 4 layers.